Welcome, friends. Our last video for this semester. Um, we're going to talk about the Maxwell equations today and wrap it all up. There's a few things that I want to tell you. So let's get right to it. Here I've got the Maxwell equations for you. Well, almost. Well, we talked about Gauss's law, flux of E through a surface, charge inside, right? Q enclosed, divided by epsilon naught. Number 2 is Faraday's law, circulation of E around a loop. This is one we just finished, is the negative time rate of change of the flux of B through the area of that loop. I guess I could put that in there. Through the loop area. Number 3 doesn't really have a name. It's kind of loosely known as Gauss's law for magnetism, but it tells you that the flux of B through a closed surface is 0. In noticing the difference here between number 2 and 3, since they both involve flux of B, the flux of B in number 2 is through a surface of a curve, the surface of a loop, whereas number 3 is through a closed surface like a sphere, right? A surface that has no edges to it, and a loop has edges to it if you consider the area. So that's the difference there. Flux of B through a closed surface is 0. That means there's no isolated magnetic monopole. There's no north pole just sitting there by itself, or no south pole just sitting there. Every magnet comes in a dipole. Okay, so that's what that one says. And the last one, Ampere's law. C squared times the circulation of B around a loop is equal to the current through the surface, or the flux of current density, if you like, through the surface divided by epsilon naught. But there's something missing, it turns out. And Maxwell was the one to notice this. And so sometimes law number 4 here has the name of the Ampere-Maxwell law, because Maxwell had to add something to Ampere's law to make it work. Reason being, let me show you. Okay, so examine this situation. We're going to go back to the parallel plate capacitor. And this is pretty, I think I remember mentioning in the early part of the class how useful the parallel plate capacitor was going to be, just thinking about it. Well, we're still thinking about it. Examine a parallel plate capacitor. So if I look at number 4, there's law number 4, as it is written, I want to examine a parallel plate capacitor, and I want to look at it as it's undergoing a charging cycle. So for whatever reason, either I have just hooked it up to a DC battery, or I have an AC source and it's putting charge onto the plates. What I am going to look at is the, let's see here. We're going to look at the plate like this. Current's coming in from this side. Negative charges are leaving that side. So let's say I goes like this. I mean, negative charges are getting put on that side. Positive charges are leaving that side. Okay, so I'm going to make this into a positive left-hand plate and a negative right-hand plate. Okay, so like that. But it's in the middle of charging, so it has not finished yet. Okay, so it is slowly, we are slowly putting more charge onto this, onto these plates. So that means that if I looked at the electric field would be some value pointed this way inside the plates, or between the plates. Okay. All right. So now what we're going to do is I'm going to take a look at applying Ampere's law. Okay, so when I look at this term here, the current through, right? That current is the flux of the current density through the surface made by the circulation loop. Right? Circulation of B is around a loop. Okay, and the current through it, like the I enclosed, is the same as saying it's the flux of current density through the surface of that loop. Okay, so what I'm going to do is I'm going to say, all right, let's do this right now. I'm going to put a loop around this wire here. So okay, just like that. And I'm going to examine the B field around this wire. Okay. Well, what this tells you, as we've studied it so far, is that because of the current going through the loop of the wire, right? In other words, going through this area right here, there's current going to the right, and then I would put my thumb that direction and curl my fingers, so the magnetic field would be coming out at the top of the loop. It would be coming out of the page, and at the bottom of the loop, it would be going in. Okay, like so. Whoops. Okay, so that's what Ampere's law tells us. But now I'm going to do something a little bit different. Okay. Now I'm going to examine, okay, I want to know what is the circulation of B around that loop. But I'm not going to choose that area. Okay. I'm not going to choose that area. There's nothing saying that I have to choose that particular area. All it says is I have to choose the flux. I have to choose a surface which is bounded by that loop. Okay. So I'm going to choose a different area. I'm not going to choose that area. I'm going to choose a different area. All I have to do is make sure that the area I choose is completely bounded by that loop. So, okay. Well, here's what we're going to do. What I'm going to do is I'm going to think of a, for example, a bubble solution. Okay. And I'm going to imagine that I suppose I dip the little wand into I dip the wand into the bubble solution, right? And right now, before I start going to the bubble, the bubble solution is it makes that surface, right? It makes that particular surface with the wand around it. Okay. But now what I'm going to do is I'm going to start blowing into the bubble a little bit. Okay. And I'm going to start expanding. I'm going to start, right? I'm going to start expanding that soap film. Okay. And so what I'm going to do is I'm going to make a surface that looks like that. That's what I'm going to do. Okay. I'm going to take, right. See how the surface here is still bounded by the loop. Okay. It starts here. It's closed all the way around here and it ends here. So the edges are still its loop. Okay. So I'm going to do that. Okay. tricky, tricky. What that means is instead of taking that shaded area, what I'm going to take is this area here. Like that. So now I'm going to examine the flux of current density through that surface, because I should be able to pick whatever surface I want. There shouldn't be some restriction about saying, well, it has to be this planar surface. Why can't I pick this surface? Well, now the flux of current through that surface is 0. Okay, I am no longer picking, oops, that didn't work. I'm no longer picking the plane surface here. This is not my surface anymore. I'm going to get rid of all of these lines. Okay, and I'm going to look at, okay, now it's as if, right, imagine that picture of the bubble. The bubble doesn't exist on the plane anymore. Right? So the current going through this loop isn't going through an area. It's not, it's missing it because my area has gone out and around. Unfortunately, what that means is there is no current density. There's no flux of current density through this surface. And therefore, I would have to say that the magnetic field circulation around that loop is 0, which is absurd. So that means B equals 0 around the wire, where I said, well, wait a minute, the B field is coming, right? I can't do this anymore because there's no flux of current through my surface. I don't have that. So I have no way of saying that there's a magnetic field here. But I know there has to be a magnetic field there. We can measure a magnetic field around a wire. And it looks like that curly thing that's going around the wire. So how can I get my new surface to replicate the experimental fact that I have a B field around a wire that carries current? All right. I'm hoping that I'm making the conundrum clear. Okay. If I do no flux of current density through the surface, then I have to say there's no B field there. But I get a B field if I just leave the planar situation, which we know is right because we can measure that B field and that's how it works out. So how come I can use this surface and it doesn't work out, but I use the other surface and it does work out? That's no good. So we have to fix this. Now, fortunately, Maxwell fixed it for us. And what he did was he said, wait a minute, what about the flux of something? Something is fluxing through this surface. Okay. Something is fluxing through the surface. It's not the current anymore. It's no current density. It's the electric field. Yeah. Can you see that? I have my surface in the middle of the capacitor. No charge is flowing between the plates, but the electric field is building. Okay. So there is a flux of E, though, through this surface, and it is changing. Right? Because remember, I'm charging the capacitor. So I'm actively putting charge onto that left-hand plate and removing positive charge from the right-hand plate, which means the electric field is currently in the middle of getting bigger. So it is increasing. If I just leave that there for a few seconds, I'm going to suddenly find I have more E flux through the surface here. Okay. So we have to fix this, and Maxwell fixed it by saying, look at the symmetry of this situation. If you look at Gauss's law, number 1 here, flux of E through a surface is the charge enclosed divided by epsilon naught. And you look at Ampere's law and you say, well, I've got a circulation of B here with a current enclosed. And you look at Faraday's law and you say, well, now I've got a circulation of E around a loop and a flux of B through a loop. Wouldn't it be nice to kind of take both of those things? That's kind of the same idea, right? Looking at the circulation of E, well, in Ampere's law here, I'm talking about the circulation of B. I don't have a flux, right? There's a circulation here in Faraday's law that's caused by a flux change. I have a circulation of B here, but there's no flux change. What if there was? This was Maxwell's contribution, in addition to kind of synthesizing at the time. 1865 was when he did this. At that time, there were about 15 to 20 different rules about electricity and magnetism. Maxwell synthesized them and brought them into 4. And he said, this is what they are. And he added this term right here, d by dt, flux of E through the surface, same surface, right? The one that's bounded by the loop. Okay, so he added that term. This is due to Maxwell. He added that term, and what does that do? It saves our butts, okay? Because now I can at least be guaranteed that if I choose a different surface, if I don't get the current through my surface, I can at least grab the electric field that's changing its flux through the surface, right? There is a flux of E through that surface, and it is changing, all righty? So what used to be a very simple problem, we've made more complicated, but we've made the idea more general now. Okay, so let's take a look at it and an example here of this. Okay, so let's run our good old Ampere calculation. If I were to have looked at the surface of this loop and said, okay, I'm going to look at, right, that surface. Okay, ignore my bubble for a minute. I can only choose one of these surfaces. I can't choose both, right? I can only choose one. The bubble isn't both, the soap solution isn't both just sitting there like a plane and also in a bubble. Okay, it's not, it doesn't work that way. If you're right, it's expanding like that. If you stop, it kind of comes back. So imagine that I'm just doing the plane for a minute, and that's a regular old Ampere's law without the term. So I would have done c squared times the circulation of B around the loop, which would have been B times 2 pi r, right? And then I would have said, okay, I'm going to look at the current going through that loop, which is I, and it's divided by epsilon naught. Okay, so this would have told us right away that our B field, as we already know, is I divided by 2 pi epsilon naught c squared r. Okay, so this is the result I need to come away with if I choose this other wacky surface that isn't planar with the loop. Okay, so now I'm gonna take this. Well, I don't know if I can really do this, but I'm gonna right. I'm gonna blow into the soap film, and I'm gonna make the bubble. Now I have no current going through this. Right now I'm looking through surface 2 here. Surface. Whoa, no. Put that back. Okay, now I'm looking through surface 2. Right, the big one, the outer one. And I'm going to say, okay, let's take a look. Now I have the circulation of B around the loop. My loop is still the same loop, right? In other words, my bubble wand is still the same thing. I still have a loop, but now the bubble goes out and I don't enclose any current because there's nothing going through this loop. Okay. So now my enclosed current is 0, but now I have to look at the changing electric field flux through the through the area of that thing. Okay, so now I'm going to do plus d by dt for the rate of change of flux of this thing. Okay, and I'm going to say, all right, the electric field, this would be, if I were to look at it essentially mathematically, it would be like this: E dot dA, right? That's my flux. That's my flux of electric field through it. So what I would say is, I would go like this: it's 0 plus d by dt of the electric field between the plates, okay, which is essentially sigma over epsilon naught, right? That's the electric field between the plates. It's a constant. Well, I mean, it's a constant for each charge. Now I'm changing the charge, right? So I'm thinking about my sigma is changing, okay? But it's that expression. So no matter what my sigma is, no matter what my charge is, that's the expression for the field, even though I'm changing the charge. And then this times the area of the flux, which would be basically, let's go back to the picture here. Can I move the screen? No, come on. Okay, which basically is the place where I'm getting electric field flux. So let's make this loop a little bit easier for me. It's a little bit less bubble-like, and let's make it a little bit squared off at the end so I just have an easy area to do flux through. Let me just imagine that it's a bit more, instead of being curvy, that it's a bit more straight up and down like that. Okay, right? Like as if it was a rectangular area right there, right? So I'll just like that, right? It's as if my balloon got pushed up against a flat wall, right? I'm blowing the balloon up, blowing my balloon, yeah, that's a good one. Blowing the balloon up, but I'm slowly crushing this side of it, so it becomes a nice rectangle, so it makes my flux calculation a bit easier. So I'm going to say that's the area that I'm looking at as the flux of electric field through it, right? We already know that this thing here is the charge on the plates divided by the area. So now, since that charge is changing, Q over A is the charge multiplied by A divided by epsilon naught. Okay, all I got to do is make these two A's the same, and look, lo and behold, I did. If you look at the area of the plate there, this is my area of my flux. Okay, so what I'm going to do is I'm going to drop those A's away. If I can get my screen to move, just dump coffee on this keyboard again. Come on now. There we go. So I dump the A's, and lo and behold, I get, obviously my epsilon naught is not changing, so I get d by dt of the Q. And lo and behold, that's the I. So this saves us. Right? Now I'm going to say that c squared b times 2 pi r is equal to, yes, lo and behold, I over epsilon naught. And I will get the same B field as I did last time. Okay, so that is how Maxwell has saved us. If that term wasn't there, we couldn't choose a surface, and we couldn't be guaranteed that we had to choose. We wouldn't be guaranteed that we could choose any surface that is bounded by that loop, but now we can. All right, so this is the new term, that one that we hadn't discussed before because we had considered magnetostatics. Yes, so we hadn't considered the changing current or the changing electric fields around the currents. We had just considered the currents to be steady. Now that we have this term, we have a complete set of Maxwell equations. All righty, so there they are. This is the Ampere. It's also now known as the Ampere-Maxwell law. Well, it doesn't really need to be because Maxwell already has this set of equations got his name on it, but it's the Ampere-Maxwell law perhaps now. certainly if you go to Scotland to learn about this stuff, if you take this course in Scotland, it'll probably be known as the Maxwell Ampere law, Maxwell being a Scotsman. So that's it. This is the set of new or new, I don't know, just that little bit at the end there. It finishes off our Maxwell equations. Um, so there's one other thing that happened here. Gosh, I'd love to go through this, but I don't know if I feel like um, throwing an extra thing on top of the fire here. It's pretty nifty, so I'll tell you really. I'll kind of sketch it out really quickly, but I'm not going to go through it because I don't think we need to worry too much about it. It's a little bit. It's it's not difficult. It's just complicated, right? In other words, every step is straightforward, but there's a lot of steps. So I don't know if I really want to go through this right now because of where we're at in the semester. If we were in a live class, I would have done this for sure, but it's different when I'm here to explain it and talk to you about it rather than just do it kind of in a vacuum here. So the last piece that I'm going to do here is I'm going to tell you that this flux, this term is actually so important that this was the term that set into motion the idea in Maxwell's mind of what electric and magnetic fields really do. Okay. You take, for example, some charge. You take, for example, a big sheet of charge and you wiggle it up and down a couple of times. Okay. And what happens is from that sheet of charge propagates a magnetic field. Okay. Because you just shook a bunch of charge. And so that creates a magnetic field in the region of this shaking charge. All right. Because I've got charge in motion now. Okay. However, if I start putting some imaginary loops in space around that, like rectangular loops, not circular ones, rectangular ones, so it makes the calculation a bit easier. If I imagine this, I'm going to look at that. I'm going to look at that loop that I have, right? Here's my sheet of charge. I'm going to go wiggle, 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 wiggle. And I'm going to look at a loop over here. And I'm going to say, pretty soon a B field is going to change its flux through that loop. Okay. Which means via Faraday's law here, if I have a changing flux through a loop, I'm going to get a circulation around that loop. Okay. Now, what I'm going to do is instead of looking at this loop, I'm going to look at the top view of it like this. And I'm going to look at a new loop, which is this way, right? Instead of having a loop this way, where I'm going to look at the changing magnetic flux through the loop like this, okay, coming through, I'm going to look now at a surface which goes like this on top of it. Okay, my sheet of charge, I just wiggled up and down. It changed the flux through here. And now I'm going to look at this, and I'm going to look at this loop on top, and I'm going to say, but interestingly, I have no charge that's moving here. I just have fluxes to deal with. And when I look at the flux of the electric field, the one that Faraday's law just induced, there's a flux of electric field through this loop, okay, which is going to cause a magnetic circulation around that loop, which I'm going to look at again in my first loop here. And I'm going to say, well, that magnetic flux is changing through this thing, which causes a circulating electric field. But that circulating electric field is fluxing through this loop, which causes a circulating magnetic field, which fluxes through this loop, which causes an electric field, which circulates around this loop, but fluxes through this loop. So do you see what's happening here? I have a changing magnetic flux through this one, which causes an electric field circulating, but that electric field circulates around this loop, but it fluxes through this loop, which causes a B field to circulate around this loop, but that B field fluxes through this loop, which causes an E field to circulate around this loop, which causes a flux of E through this one, which causes a circulation of B, which causes a flux. Wait a minute. We've just created something that travels away from this sheet of charge. Okay. We now have a butterfly, right? We took our caterpillar of static fields And now it's a butterfly. The fluxes, these changing fluxes, these two right here, okay, are causing each other, essentially, right? I get a flux change of E that gives me a circulating B, but I get that circulating B, like look at it through a different loop, it's a flux of B, but that causes a circulation of E. But I look at it through this first loop, and that circulation of E is now a flux of E, which causes circulation of B, which causes a flux of B, which causes circulation of B, which causes, and off it goes. Electromagnetic waves are what Maxwell realized he was getting here. Okay, these two things right here cause you can show from these two right here, this one and this one, we can show the existence of electromagnetic waves. Okay, and they propagate away from my vibrating sheet of charge. They're gone, right? They have nothing. They have detached themselves from my charges, and they are over there now, and they're self-generating. Okay, they self-generate because the flux of one creates the circulation of the other, which creates a flux of that one, which creates the circulation of the other, which creates a flux of the first one. All right, so they are self-propagating. That's key, because if they didn't do that, they wouldn't be able to travel, right? We wouldn't be able to listen to radio. Okay. The question is, what speed do these electromagnetic waves travel at? Well, it turns out that if I go back over here, come on. If I go back over here to look at what speed is involved here, there's only one speed involved here. It's that one. All right. All right. These things travel at speed of light. Okay. They travel at the speed of light c. Maxwell thought about this. He said, that's strange. Why should electromagnetic waves travel at the speed of light? Now, I need to take you back in your minds to the 1850s. Think about it. It seems like it was yesterday. We have this idea in physics of what's kind of called unification, okay? And we take two ideas and we realize that they're actually the same idea. They are two different facets of the same thing. And there have been many great unifications over the course of history in physics, and one of them was done by Newton, when Newton showed that gravitation between Moon and Earth was the same thing as gravity, which pulled stuff down here on Earth. That was a major step forward. Okay, it was at that point when he showed that the laws of moving objects and objects under the influence of gravity here on Earth were the same as the ones that influenced the moon, and they were the ones that influenced what he called the heavens. And all of a sudden, the laws of the heavens were the same as the laws down here on Earth, which was an absolutely roundly rejected idea by those who were involved in religion, in churches at that point, because that was in the 1600s, okay, in the really late 1680s. It was about the 1660s, really, more like, but he didn't publish it until the 1680s. It was repulsive to the church, and of course the Church of England, right? Because that means that we down here on Earth are subject to the same laws as those up there. And that's not okay, because up there is heaven, and heaven is perfect, and only perfection exists up there. And we down here on Earth are dirty, disgusting beings who do horrible things, but none of that happens up there. It's perfection up there. Nothing bad ever happens up there. But all of a sudden Newton said, well, they have the same laws as we do. And that was one of the unifications, a step forward. Right here is another one. Maxwell has now unified, okay? He has now unified the fields of electricity, well, that's a comma, but it's kind of high, magnetism, and optics. Okay, I'm going to read you. I wrote a quote of Maxwell's here. Let's see. Here it is. Okay, I'm going to read you this quote from Maxwell's paper that introduced these equations that he wrote to the Royal Society. Maxwell said, here I go, and I quote, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena." Okay, end of quote. So what did he just say? Hard to say, right? What did he just say? We can scarcely avoid the inference, which means if you don't think this is true, go take a running jump, okay? That light consists of the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. What he's saying is light is a result of transverse undulations, right? Oscillations, waves of electric and magnetic fields. That was the unification. The idea that light is an electromagnetic wave. That was not known. This is the first time that somebody has realized that light is an electromagnetic wave, something you have probably known your entire way through this class. But this is it right here. And it's because of that term that he added to Ampere's law. If he didn't have that term in Ampere's law, then A, our B fields would be wrong, and B, he never would have figured this out because the fluxes would be hard to, you wouldn't have a flux to calculate for the electric field. So this is the big key right here, okay? This is the thing that tells you that it's light that we're talking about. As it's propagating away, it has become light, and we call light the electromagnetic wave, okay? So that was the big thing. That was the big thing that came out of this. And that's why the speed of light shows up in Maxwell's equations. And it tells you, wait a minute, these things are light. They travel at light speed and they are light waves. Okay. So that's the big thing. This is no longer, these fields are no longer something else, right? Optics is not just this other thing. It's this. Okay. And now you can go in and show that a lot of the things, if you've had 4C already, you can show that the idea of, for example, the index of refraction. Well, the index of refraction is related to the dielectric constant, right? How insulating is this material? You can show that a number of you go right in. We can talk about diffraction, interference. These are all wave phenomena. This is why, okay? So that's that. This means that our study of classical physics to this point, if you have had, well, you've had to have 4A. So our little quick summary of classical physics here is our set of laws now. Okay, we have Newton laws, Newton's 3 laws of motion. We have laws of conservation. We have actually 3 laws of conservation from mechanics. And we have the law of universal gravitation, also, of course, due to Newton. Those of you who had 4A last semester, you may not have had the time to have gone through universal gravitation, which is a shame, but nonetheless is highly worth your while as a field of study. So these are from 4A. Okay, those are the 7 laws that you can study in 4A. Newton's 3, 1, 2, and 3, gravitation, the force of gravity being two masses multiplied by and then divided by the square of the distance between their centers. That's Newton's law of gravitation. Notice how it bears a strong resemblance to Coulomb's rule. And then, of course, you have conservation of energy, conservation of momentum, and conservation of angular momentum. All right, so now we have Maxwell's equations to add to that. Okay, there's 4 of those. We now have the 4 Maxwell equations. And if you've gone, so there you go, that's the end of us. And then if you go into 4C, it turns out there are 4 laws of thermodynamics. Which you can talk about. One of them actually is the same as the conservation of energy. So there's actually like one of those. I should cross this out and say now there's 2, and that one comes down here to go with these 4 here. So those are them. And I hope you've enjoyed the class. It's been really, really strange, and definitely not what we wanted. But I think what a good thing to take away here is we got it done. You know, we even in a time when it seems like, you know, school and going to school and teaching and learning aren't really going to happen. At least we had some medium to do it. And honestly, you can thank Maxwell for a lot of this, because if we didn't have Maxwell's equations, none of this would have been happening. None of this video stuff would have been possible, right? Anyways, I'm going to sign off. This is the last instructional video. I'll do one more on the review of the celebration too, so we can get that out of the way. And I guess that's it. Thank you, folks, for your attention and your hard work, and honestly trying to do it in this setting. I know that it's a struggle, and I know it's a struggle. So thanks for struggling through it. All righty. Well, that's that. Happy rest of your day, my electromagnetic friends.